Welcome students to my 20th lecture in the series of this NPTEL course on farm machinery. This is entitled as Embedded GPS Integrated Variable Rate Fertilizer Applicator. Well, before I say get into details of this, I must tell you that we had also discussed of the DGPS Integrated Variable Rate Fertilizer Applicator, wherein actually we wanted to tell you as to how we should be in a position to identify what is the amount of nitrogen which is already present in the soil at any particular point of time. It could be because of the previous crop, there could be nitrogen fixation because of the previous crop if it is a leguminous crop, or because of the residual amount which has been applied in the previous year or years like that. So, we wanted to have a precise amount of this fertilizer, particularly urea, particularly this we wanted to give with respect to nitrogen application. So, we wanted to check how much is there in the plot, in a given plot, and what should be applied. Now, this will be also varying from location to location in a plot, and that is why we had discussed in my previous lecture that we would like to follow a procedure of finding out what is the amount which is already present. Now, there are two ways I had told earlier. One is a sensor based approach, direct online, the other is map based approach. So, we discussed about map based approach because sensor based approach so far we have not been in a position to design that or develop that, although people in other locations are trying, we are also trying, but we have not yet as successful. So, we are not in a position to talk about that. But definitely this map based approach which people have tried at different locations, we have tried at IIT Kharagpur also, and we have gained a greater amount of success in this. So, in the map based approach we said that we would like to have an information about the condition of the soil of a particular field, wherein we want to apply the amount of nitrogen through urea. So, we had as discussed earlier, we had taken samples, soil samples, real soil samples from the field, large number of samples, then we identified the various constituents of this NPK. We mostly talked of N, but we definitely found out also P and K of the location, and then you might have if you see my previous lecture, you will also see that I had graded that in each of the grids what was the amount of nitrogen present at those locations, and corresponding how much of urea was present over there. So, in the embedded, and there we got a certain type of machine, wherein we had the GPS which was rover GPS which were there on the tractor itself. There was another which was there at the base, and the system which was there which was connecting the fertilizer application system. Now, since the cost involved in all these was quite high, we wanted to think of further innovation in this, and with the help of our friends and with the help of our knowledge, we read more about electronics, and we thought of having introduction of embedded systems, and then we have modified the same unit. So, today I will discuss about that, where is the modification and how far this modification has been in a position to give you a cheaper unit, because ultimately we must produce units which are cheaper and which we are in a position to produce at our location or in our country, so that we do not have to borrow from anywhere else, and we should be in a position to produce large number to in fact export and give it to other people. So, in this context this lecture has been prepared. So, let us go one by one. Well, what is this embedded system, you would ask me. Now, look, as an electronics engineer many things are needed, but as an agriculture engineer I went into finding out what are the things which are basic importance to an agriculture engineer to understand. We may not be in a position to know the much details of the electronic hardware, etc., but definitely we will have some idea about what it is and what is its job. So, embedded system is a computer system with a dedicated function within a larger mechanical or electrical system, often with real time computing constraints. Now, it is already written. Now, why I am saying also, and I have written here, so that when you see the lecture at any point of time, you can come back and have these definitions known, but then I have written here for your benefit, so that we can follow and have a dialogue here for this lecture today. Embedded is a complete device, often including hardware and mechanical parts as a part of a complete device. What are the components of this embedded system? Well, what are the hardware? Well, you might have heard of this. It is at our level, it is very essential to know this part. We should have our other colleagues who could help us in finding out the details of electronics for it, but then definitely we must have some idea when we are thinking of designing such a system, when we are thinking of agro-electronics, and when we are thinking of Internet of Things into agricultural application. Definitely we will have to have some idea about this. So, the hardware consists of processor, the timer, port, memories, input output devices, sensors. Main application software, we do need to, you will have to have the software created for the job that you want to be done by this. It could be to perform a series of tasks or multiple tasks depending upon what you want. So, this the component of application software. Real-time operating system. Now, this real-time operating system defines the way a system works and supervises the system software. It will supervise the system that whether everything is going on in proper way or not. Now, if you see the figure which I have given on this side, the whole details are given over here. Now, you can see the software is the base which will in fact do the job, the single task or a multitask that you want, it will do the job. So, it is there at the center. The embedded computer that we are calling of hardware, and link to other systems. We will definitely link to other systems which will ask it to do the job. But then there are certain inputs. So, we will have certain input variables to this system, and there will be definitely certain output variables which will come out of this, and hence there will be a user interface. This user interface will help us that what sort of data, what sort of parameters which need to be embedded into this apart from the input variables, how do we get. So, this is what we talk about the embedded system as such. If you want to know more and more details of this, well, you can open any electronics book and you can have about these details. But what is important from an agriculture engineer's point of view is to understand the application part of it. We are more concerned about application. They are better hardware engineers, but then what we are concerned is how that knowledge can be introduced into our application, which will give us a precise application of this, precise application of the item which I want to do, precise time and the operation at which I want to do. Application of embedded system in agriculture. Well, this is worth giving you, because then as an agricultural engineer or a designer, you may not be a farm machinery engineer, you could be dealing with maybe soil water, you may be dealing with some other machines and things like that. So, the use of this or the application of this system is enormous. I have just jotted down into these details. But then details, if you go into details of each and every aspect, you will find that the application is enormous. The water management, yes, we would like to manage water. We know that water is a scarce commodity, day by day we are losing water. So, how best we can manage water, how we can utilize the embedded system to manage water at a location, what is the available water at that location, what is the amount of water available at a certain depth of the aquifer, and what is the catchment area, how do we manage, what sort of GPS location we have, how do we manage that. So, you require the application of this embedded system there as well. Then soil monitoring. Soil monitoring sensors, we need to know about the soil's moisture content, we would like to know the nutrients contents of the soil. These are important things which we will have to have, and for that, because the soil is there at various locations, and then from satellite we have information about every field at various locations. We would like to know what is the soil type, what is constituents, what are the other details of this, so that we will know what sort of crop can be grown, what will happen if the moisture is high, what will happen if the moisture is less, what sort of equipment can be employed onto operation for doing a particular field operation, things like that. These are essential. Drones for field monitoring. Now, embedded system can also be there on that, because when we have a drone, well, need not to say that a drone is now everybody knows for the various applications of taking photographs and then finding out the diseases. We are also working on various aspects of utilization of drones, identifying things. Now, I saw in one WhatsApp video that people are also using this for transporting or supplying food materials or the food tiffins, etc., several aspects of this. So, here also you can utilize this embedded system. You can write a software which will talk of what to do and where to do. Accordingly, this drone, which is nothing but also a robot, form of a robot, which will do the job. Then machines for routine operations. What are the various machines, the infrastructure requirement, the road making or the earth moving machinery, etc. If you can have the embedded system which will minimize the cost of various other items or components which will be there in the whole gamut of the system. That is why we say that embedded system, if help is taken, then it will be a cheaper system as compared to any other system. So, I wanted to show you that what are the various major applications of embedded system. If you go into details of each one of them, you will find much more details. Well, it is important, because I said in the beginning that we had discussed about the differential GPS based variable rate fertilizer application system earlier. You may mark that this is a system which has an IPR and it is developed at IIT Kharagpur. So, this is important here. Now, this system has been developed. We wanted, as I discussed initially, that we wanted to make the unit even cheaper, because ultimately our aim is to make it simpler, cheaper machines, compatible, and then this can be used by the farmers, can be purchased by the farmers, and hence we went into the embedded system. So, when we have an embedded system, what are the things that we get, what are the things we add, what are the things we delete from the total component. So, let me go to the next slide first, and then I will come back to this slide. Yes. Now, if you see this particular slide here, with the VRFA system, earlier system, here is the earlier system. This is the earlier system here, where we had the satellite information from here. This is the rover GPS, then this is the base GPS at the base of the location where we are doing this, and this is the system which is there. This system is then connected with the fertilizer applicator system. You can see here the furrows and all that is connected to the 3-point linkage here of the tractor. Now, you see this was the system, and I would like to draw your attention towards what was there in that system. Well, just see on the other side here that GPS rover, then GPS base, which are these two here. Then the computer which was there, yes, this is the computer which is there. So, you have certain cost for the computer, the microcontroller, then the DC actuator motor, because this DC actuator motor will now then do the job of changing the location and the exposure of the fluted roll into this system. The rake and pinion arrangement, well, the rake and pinion feed soft with the fluted roller. Now, here when we talk of this, we must see the ground wheel, because we have taken power from the ground wheel. So, when you take power from the ground wheel, seed fertilizer chain driven unit, we will talk of the details of this power transmission at later stage, but then I am talking of those details here. Then it goes to the feed shaft volumetry mechanism. Now, here this DC motor will do the job here, and then the variable rate application will be applied, or the the amount of fertilizer to be applied will be activated by the end of this, and power for the transmission is taken here. So, ultimately from the in location of the GPS rover and compare with the GPS, we will have an accurate information as to where we have reached with when the tractor is going into the field, and then the microcontroller will talk of the conditions and find out, and we will have the software. That software will identify the grid, etc., and then the DC motor will be asked to do the job, and then it will ultimately through the power transmission unit, it will indicate the feed shaft with the fluted roller, change the position of the fluted roller, and then the variable application will be available to us. Now, this is that part of it. Now, in the next system that we are to call embedded system, what did we do? So, I will show you what we did. Now, here you can see here that we do not have this part, we do not have this part, we do not have this part. Now, you can see that so many things have been minimized. These are virtually eliminated by the system. The system which I want we wanted to indicate, this is you can say a higher version of the earlier unit, where we had the GPS based system. Now, here we have a GPS module system, variable rate system. Here if you see the working microprocessor, microcontroller unit, the relay is there, DC motor is there, fluted roll and potentiometer. So, these all will do the same thing. Display will indicate certain aspects, display will tell where you have reached and what is the available nitrogen at that place, and hence the urea and how much urea you should apply, so that the exact amount which is required at that position will be applied. So, the same thing which was done earlier here will be done by this system, but then with lesser number of components, and many of the components have been embedded into one. So, if we go back to the previous slide, then we will be in a better position to compare those systems at this point of time. Yes. Now, you can see we have discussed this part. Now, what we can get here is that if this is the balance here, now you can check in this in LCD touch screen display of to 2000, unblocks GPS module is rounded off to 2000 rupees. Then Raspberry Pi 2 model B has a rounded off price of 3K and Arduino price is 1.5K. Now, and what is here? The GPS, which has a price of about 4.5, because you need one at the base, one at the rover there, then laptop, which is about something of the order of this. So, you can see that how much is the difference between this. This is 2000, this is 2000, 4000, and this is 3000, about 7000, and this is 8500 roughly. So, a location of about 4,000, 4,80,000 to 4,50,000 here and 30,000. So, we are getting a large reduction in this, and that is why this is shown that this is in this way. Here you are using more money, or you are requiring more money for the same job. Here you are requiring, here you are requiring less money, I am sorry, here you are requiring less money, and here you are requiring high money when you have DGPS like this. Now, these are the systems which when we compare with the previous one. Okay, let us now proceed, because we have now compared what is the DGPS which was earlier and what is the embedded system which we have, what are the things we do not need, etc. Of course, soil analysis, the methodology. Here also it is needless to tell you that the moment we want to utilize this system, what it does, in fact, it cuts down those items which we do not have, but the basic system remains that you need to measure the amount of soil which is there, in the grid, the nitrogen which is there, and the amount of information that you need from a particular field about the soil. That details are required anyway. So, the soil analysis is required. At Kharagpur, since we did the work at Kharagpur, we had made 32 grids of this size, 5 meter into 4 meter side, and this is the grid. One grid is this, another grid is this. Now, where are the locations where you can take soil samples? Now, this there are a lot of debate. In the previous one, people have taken samples at the corners here, here, and one from the in the center. Now, in this we decided that no, this may not be representing that. So, we wanted to have a larger zone of soil which is covered by the samples when we take diagonally. So, we thought that if this is the, say for example, if I talk of this, then there will be zone which is covered, this it covers this zone, this covers this zone, this covers here, this covers zone. So, more or less we will be, this is what we think, and possibly we got also the information. In fact, we compared that when we have these 4 locations at the 4 corners and 1 at the center, and take an average of that, and with this we found that there is better accuracy of the data information that we got here as compared to that one. So, that is why we decided this to be the grid, and this is to be the process of collecting the soil samples. Those samples have to be taken to the laboratory for finding out this. Now, it is a different question that how much sample you will do this, and if this system has to be operated, the machine has to be operated, how much time, when, and all this information has to be had, has to be taken before and given. Those are a different aspect. We will not talk of that at present, but what we will say that in case you have found out the information, then you can use this machine and get the benefit of that. So, we will with this premise we are going ahead. Well, this talks of the information. Actually, what is the information with respect to the grids? As I said that we made 32 grids. So, you can see here that 32 grids, from grid 1 to 32 grids we are, and at each grid we had found out what is the amount of nitrogen which was available through this. You can see this. So, we know that about in urea 46% nitrogen is present. So, with this we know how much of urea is there in a particular at a particular grid. Say at grid 1, this is the amount of urea which is already there, this 19. At this is this. So, we had decided, our design was such that we can give up to 400 kg per hectare of the urea to this system. This is what we had decided, because of the limitations of the size of the fluted rolls and the size of the machine which we had taken. So, we had said that a minimum of 5 kg to a maximum of 400 kg or so. You will recall that in my previous talk also I talked of this, and here also I am saying that up to a maximum of 400. So, with that base of 400, we had written the software, the user interface, which will tell us that if we go to the grid, if we reach to a particular grid, what is the amount which is available there and how much is to be given. So, automatically the system will do, and we will show you how it does. So, the data points, these are the data points urea. You can see in this one that each data point, there are various data points here. At each point here we are in a position, the available ones are given with this this color, and the urea to be applied is given in this. And I have talked of the samples, etc. So, this data tells us what we got at IIT Kharagpur. You will have to, if you want to do this experiment, you repeat the experiment, or to verify the experiment, you will have to follow it at your location as well, in order that check what it happens at your locations. Embedded electronic control unit. Well, some details of this. Actually, as I told you that we as an agricultural engineer, you must have an idea what is happening inside, what are there the constituents of this embedded system, what does it do, and so that we know that these are the informations coming because it has these inputs. So, if you see the microprocessor, GPS module has certain things. See this GPS module. Now, this has the microprocessor, system on chip, and then the enemy, the parse the enemy sentence, there will be a string in which the details of the information which will be available to convert the latitude, longitude to LTP, which is local tangent plane, because local tangent plane of that area in the field which we are talking of. Then calculate the shortest distance of the current position for the field boundary. It will talk of always the shortest distance, because when parsing of data will be required by the software, it will tell as to what is the shortest distance, and accordingly it will find out the coordinates of that point. So, that is very important. We must know the coordinate of that point when parsing of data is taking place by the system. So, determine the grid. So, what will happen? So, we need to determine the grid location or where it is. So, where there it will display user input here. In fact, this is going here. So, it will display the user input. It will display the information and then say what is the amount of user input which is to be given. Then match the grid with the fertilizer requirement. That this has to be matched with the fertilizer requirement. How much is the requirement? Okay. So, then it will go to the microcontroller. Now, this microcontroller, well, which will have direction of direction signal to the motor via relay, feedback from the potentiometer, interrupt back to processor, and then information between mechanical fertilizer and the applicator potentiometer. Applicator and the potentiometer, the job will be taken up and the whole thing will be done. We will show you how these are being done actually. So, the embedded electronic control unit, we have, since this is done at our place and we have the IPR issue. So, we are not telling you all the details of the circuit as such, but we are definitely telling you what we are doing, how we are trying to do this thing. Now, this slide shows some of the locations of what it is in the field, because we wanted to do in the field. We have done this test in the field. Now, figure A here, this shows the setup or the machine system in the field. There you can see here that we have talked of the lever. This is the lever here. Now, this is the lever which actually will move and change the exposure of the fluted roller while we want to have a change. And now, this will be done on the advice of the DC motor which is there. That motor has been accordingly, this has been fixed at 120 RPM. This fixed because we want certain amount of information, certain amount of chemical, the fertilizer to be applied. So, we have set all this thing. Then we have the relay system which will tell us as to how much is the gap and what is the what are the systems which are working with respect to the others. Then the 2 is the 3 is relay, 4 is microcontroller, where this is the microcontroller system over here. Now, there is a TFT LCD display, this LCD display over here, which will tell us what is the amount of information which is displayed in this TFT display. This is about thin film transistor LCD display. Now, figure B shows the fertilizer collected in jeepers. See what happens, when we are testing in the field, we do not want that this should be lost. So, we have the jeepers here, you can see that jeeper bags we have kept to each one of these, and then we have collected while we were testing, so that we can test an unnecessary waste, because once it goes to the soil, you will appreciate that we will lose that. So, we do not want to do that. So, we wanted to have those things. Figure C shows the lever which marks the movement of the fluted roller. So, this is the lever. I have shown you the lever in the previous figure also, but this is the lever. So, this lever will move. When we show a video, you will see how it moves. So, we will move to the next and have a look at the field testing. Well, field testing of the unit. Now, we have discussed a lot about this unit now, and all the locations and the systems which are there are indicated here. I can show you again, the electronic controller is here, the embedded GPS module is here, then the DC motor is here, there is a battery which is running, giving the power to the whole system, and then the machine is working in the field. So, we will show you the video of how it works in the field, how it changes the location of the exposure of the fluted roll. Well, you can see that this particular location, it has moved. This lever has moved. We have changed. You might have seen that the speeds are there. The lower speed, higher speed. You have seen the speed, and then this lever moves. You can again see that the lever is moving. If you watch properly, you can see that this lever moves, and it is on the advice of the motor which is there. Well, comparison of data, 3 different speeds. As I said that we have tested in the field condition, and we tried at 3 speeds in the field at 2 km per hour, 3 km per hour, and 4 km per hour. And then this is detailed information about that. We have shared with you so that you can have a look at it and understand the level of accuracy or the level of effort that we have made in actually field testing of the system. Well, if you compare this, the actual amount dropped and the required urea, you will find that R square is coming about 0.9528, and hence you will appreciate our effort that yes, the system is working all right. But then there are certain hiccups, because when we compare the errors with respect to at different speeds, at 2 km we find that the error is very less, about 2% error. What is the fertilizer actually dropped and the fertilizer to have been dropped. This. Then in 3 km this is to have been dropped, but this much has been dropped. Then at 4 km this is to be dropped, this has been dropped. Now that means there is a speed, there is some mismatch between the speed at which we are moving. So we are further working on to this and trying to see that it should not be dependent on the speed. Possibly we have to do some more manipulation of the speed, forward speed, and the movement of the exposure, etc. So you can find that this value is very high. So as such, we find at 2 km if you move, which is generally about 2 to 3 km per speed per hour is the speed at which we operate these equipment or these machines, you will get a reasonably accurate delivery or accurate application of the fertilizer. Thank you very much.